All right. Well,
Uh,
welcome back to our last talk of the day. This is Siddharth Bhat, and he's going to talk to us about certified decision procedures. So go ahead, take it away.
yeah, thanks. Hey everyone, I'll be talking about some decision procedures we've been developing here over at Cambridge at Tobias Grosser's lab. And yeah, we're sort of generally interested in compiler verification, so I'll sort of talk about what we've been up to. Um, cool. Okay. But first off, to start with, a huge thank you to all of my collaborators. So there's Leo and Chris Hughes and Tobias Grosser, and it's been a lot of fun working with them to sort of to build this stuff. So yeah, I just wanted to say thank you to them. Right. Okay. So let's kick it off. Um, yeah. So right. So when it comes to compiler verification, one of the questions we're interested in is to know whether two programs are equivalent. So here, for example, I have a source program that says, that says that it's going to compute a value by essentially dividing a number by 8192. And then there's a target program that's going to compute the same thing by shifting the value, right? And so how to say, a moment's thought will reveal to us that these two programs are equivalent, but how do we really know? And so like typically, if you're sort of developing a compiler, and in our case, the compiler we're interested in developing on and verifying is the LLVM compiler infrastructure. What you would do is to use some tool like Alive, where essentially Alive is a tool that's used within the LLVM community to sort of check these kinds of transformations. So what you'll do is to plug these source and target programs into Alive. And then Alive will say, okay, yeah, you know what, this transformation seems to be correct. Right. So now suppose you made a mistake and you try to convert division by 1 into shifting by 13. If you were to ask Alive, hey Alive, are these two programs equivalent? Alive would then reply with this thing where it would say, hey, you know what, this transformation doesn't verify. And I provide you an example where the source program produces an output of 1, because if you divide 1 by 1, you get 1. And the target program produces a value of 0, because if you shift 1 by 13, you get 0. Right. So like having such tooling is incredibly useful. But how does this work? Maybe to the surprise of very few people in the audience, like maybe before that, like Alive is nice, and like Alive is sort of, it's used habitually within LLVM, right? So it's not like, how to say, it's not like some kind of researchy tool that exists, but it's more like every commit into LLVM that changes the optimizer repeat, like always uses Alive to sort of justify these things. And so if you sort of go look at the LLVM code base, there are basically thousands of commits that use this kind of tooling. So having this kind of tooling is like super valuable. And we'd like to develop formally verified versions of this kind of tooling, because for us, sort of the ultimate goal is to be able to write a verified compiler. And being able to verify these kinds of transformations is sort of like an important building block to be able to do that. Right. And so the way in which it works is it sort of takes this problem description, and it converts it into some kind of problem over bit vectors. And once it does this, it then queries an SMT solver in order to check that that the source program, now expressed in terms of bit vectors, always produces the same result as the target program. Of course, this is sort of sweeping a lot of details under the rug, because it's kind of like, in reality, LLVM has complicated semantics, and so the translation to the theory of bit vectors is not straightforward. And yeah, like how to say, there's a bunch of research on this, but that's not the part I'm interested in. Sort of the part that I'm interested in is to really say, okay, now that we have this bit vector problem, how can we verify it in a way that's trustworthy, right? And so yeah, so in some sense, the core engine that's used is a bit vector SMT solver. Yeah, and right now, and as Leo said, like thanks to Henrik and lots of folks in the fro, we now have like a really good bit vector solver in Lean called BVDecide. But somehow, for us, even BVDecide doesn't really solve the problem, because when you're implementing a compiler, you don't really want to implement a rewrite for 32 bits or for 64 bits or something. But instead, what you want is to have a rewrite that works on any possible bit width. So now, so now it's like, the kinds of theorems you're interested in proving are not about bitvec 32 or bitvec 64, but it's about like any sort of arbitrary widths that you have. So in some sense, we're no longer dealing with the theory of bit vectors, but we're dealing with the theory of parametric bit vectors. And so, right. And so this is the theory for which we want to have solvers for. And that's basically what we wound up developing. So like right now we have like a couple of solvers, which are sort of developed in Lean. They're all mechanized. They work by like a reduction from this original problem to some decision problem about automata. And essentially, you can basically like use these solvers in order to actually decide problems about parametric bit vectors. So I'd maybe like to spend some of the time describing like at a somewhat high level how these algorithms work, because I think that's interesting. And then maybe to give some sense of what where we're going forward with this. Cool. Okay. So right. And so like for an example of the kind of theorem we can prove, this is like a fairly typical example where you want to say something like, for all possible bit widths, show that the bitwise AND operator is idempotent, right? Right. Okay. Yeah. And so right. So how does our tactic actually work? So the way we actually view this problem is the following. So essentially, the way we think about a bit vector is, instead of thinking of it as some kind of finite list, we view the sort of universally quantified bit vector as an infinite bit stream instead. So in this case, like the first bit, that's going to be x naught and x naught, which we know is always going and so right. And so we know that at the sort of 0th bit, because bitwise AND is idempotent, we can check that at least at the first bit, x and x does indeed equal x. And then we can do the same check for the second bit and the third bit and so on. And so somehow, and so we convert the problem of checking whether x bitwise AND is idempotent into checking whether this other sequence is always going to be true. But like, how do we make this sort of decidable? So in some sense, what we do is we encode all of these as automata. So for example, if you think of the bitwise AND operator, you don't really need to keep any state in order to compute the ith output bit given the ith input bits. So for example, in this case, when you see 0 and 1, you know that the bitwise AND is 0. Okay, then you grab the next bit, you see that the inputs are 1 and 1, so the output is 1. And for another example, if the inputs are 1 and 0, the output is 0, and you can sort of like keep going this way. So this gives you the automata which receives inputs 1 bit at a time and produces the output 1 bit at a time. Right. And then, so the other operator that we have is the ability to compose automata together. So we have this generic automata that takes any two arbitrary inputs A and B. And we also have the automata for X, which says that if it receives an input 1, I produce an output 1. And if I receive an input 0, I produce an output 0. So what we can then do is to compose these two automata together to get the automata for X bitwise AND X, which basically loses two transitions where the bits differ. So this gives us an automata that says, okay, you know what, when the input is 1, the output is 1. And when the input is 0, the output is 0. Cool. So we can decide this much. So now the next thing that we're interested to decide is actually bitwise equality, right? Because we want to know whether the two bit vectors are equal. For this, the automata is a bit more complex. And, I'll walk you through it. Right. So let's start, assuming that sort of in the two bit streams, we have both A and B as 1. And then we say, okay, you know what, I'm going to output a true. And I'm going to stay in my state that says things are true. And maybe for the second bit also, the streams are equal up to the second bit. So, it stays equal. But now on the third bit, the two streams start differing. So we then transition to a state where we now say that, oh, you know what, the bit streams are now no longer equivalent. Right. And so now, regardless of what happens, even if we see bits that are equal, like we know that because we disagreed at a prior bit, we're going to continue disagreeing. And so this is one of those cases where you actually need to maintain some state, right? Because somehow, like, if you've disagreed before, you're going to continue knowing that the bit streams are disequivalent. So that's sort of what the automata for actually checking equality of two of these bit streams look like. And so therefore what we can now do is to compose all of the automata together. Like we have an automata for x, we have an automata for x and x, and we have an automata for equality. And so then what we wind up doing is we just compose all of these automata together. So we get sort of this as the final automaton that essentially produces the stream that we're trying to understand. And now, the original question was, is this equality true? And that's now reduced to this question of, does this automata always produce true? And so, at least in this case, we can clearly look at the automata and we can say, yeah, like clearly, regardless of whatever input you give it, it's always going to produce true. And so therefore, we've essentially proven the correctness of the original statement we started out with. Of course, like in this particular case, what I'm actually doing is cheating, because I say by visual inspection, but that does not really allow you to write a tactic. So instead, what we wind up doing is we wind up like sort of actually writing, a library for doing automata theory, and we sort of like implement model checking algorithms, which can sort of actually check that, for an automata, its output is always going to be something that you want it to be, basically. So we have mechanized implementations of like two styles of doing this, essentially. So that's like in a nutshell, how this particular tactic works. And like you can even encode addition like this, where you have a state that corresponds to the carry state, essentially. So for example, if you want to add these two things, then you start off by assuming the carry is 0 and 1 plus 0 is 1. But then, if you try to add 1 and 1, you produce the output 0 and you move to a state where the carry is 1. So now you have your carry bit that tells you that the carry is 1. And so this way you can sort of even compute, like addition. And similarly, like you can, how to say, you can essentially also compute things like conjunctions and disjunctions of predicates. You may ask, okay, what is actually automata representable? What can you decide in this framework? And essentially anything that's bitwise, follows from the similar thing that I showed before. We also have equality. We have addition by building an add carry circuit, and we also have negation, because you can encode negation as a bitwise not plus 1. And similarly, multiplication by constants and all Boolean combinations of predicates. So like roughly speaking, what this lets you decide is essentially any collection of bitwise operations mixed with like any collection of linear operations, right? So that's what you can decide. And also furthermore, because we can decide all Boolean combinations of predicates, you can have arbitrary hypotheses or whatever, and that's perfectly supported. So the algorithm is both sound and complete, which is quite nice. Like in that, so that if you're within the fragment, if you ask the solver, it's definitely going to solve it. And furthermore, when it doesn't and finds the counterexample, that you can trust it, which is a nice property to have. And so so that's nice. Then there's sort of this other solver which works on a much smaller fragment, but this solver is much faster, and the idea of the solver is kind of cute. So maybe I'll just quickly explain it. So this solver works on a fragment called mixed Boolean arithmetic, where this fragment is the following. So the inner terms that you have, they can only use bitwise expressions, for example, XOR and bitwise and your outer terms can use linear expressions. So you have a mixture of arithmetic on the outside and Boolean operators on the inside. And the kind of interesting observation that really powers this solver is a kind of neat linear algebraic theorem that says that such an identity can be true for an arbitrary width if and only if the identity is true for width one. And so yeah, so we wound up mechanizing this and proving it, and this is also sound and complete, so that's quite nice. Yeah, so this solver also does the right thing for this particular fragment, and it tends to be much faster. Yeah, and so and I mean, how to say, and at least in our experiments, like, the solvers do seem to scale up to moderately sized problems. And I mean, when it comes to sort of compiler verification workloads as well, they're not the greatest, and they do wind up timing out, especially as the problems get larger. But we've been trying to work on making our solvers scale better at the moment, and I'll get to that. So the thing that we're sort of currently working on, or one of the things that we're working on, is it essentially the model checking algorithm that I told you sometimes is a bottleneck. And so George Rennie, who's another PhD student at our group, he's working on using a much faster algorithm. And so yeah, and so essentially, we're writing verified certificate checkers for this particular kind of certificate that's also useful in let's say hardware model checking. So that's another thing that we've been working on. And also in terms of theory, yes, yeah. So like, like, there is a natural question to ask, which is in some sense, like, are our solvers somehow, are we really deciding the largest fragment possible? And so yeah, and so, like, at least in terms of decidability results, we know that as soon as we have bitwise operations, linear is really the best you can do. In that, as soon as you add multiplication, the natural numbers become definable. And so therefore this entire theory becomes undecidable. But then, on the other hand, there are sort of other operations, things like bit vector appends, and maybe that plus the linear theory is undecidable. We don't really know. And so yeah, so that's something that we've been thinking about, and trying to figure out as to whether these sort of, like, other fragments are actually decidable or not. So I guess that's yeah, that's sort of the view that I wanted to give you, which is we're interested in mechanizing compiler problems. And so yeah, we've been working on these kinds of decision procedures. If you have uh, theorems that you'd like to decide that live in this fragment, please do contact me, because yeah, I mean, I'm always looking for more problems to solve. And yeah, so thank you. Questions?